In the last section we talked about sequences, and so in this section we're going to talk about summation, notation, and series. And so when we're talking about summation notation, okay, there's a convenient notation for the sum of the terms of a finite sequence. It's called the summation notation or sigma notation because it involves the use of the uppercase Greek letter sigma. And then so here it is. So that's what's used for your summation notation. Here's the definition. The sum of the first n terms of a sequence, right? So if you're adding up the first n terms of a sequence, it can be represented by this formation, right? And so I is the index of the summation, okay, n is the upper limit, and 1 is the lower limit. So basically, what you've got when you're looking at this summation notation, this part is the explicit formula, right? This part is going to be the explicit formula. The a sub I, that's where your explicit formula is going to be. And so this bottom number here, that is the lower limit. So that's the number that you start adding together, right? Okay. Typically it's 1, but it doesn't always have to be 1. Okay, so your sum doesn't have to start with the first term in the sequence. This could be a different number. And then n, that's going to be the ending term of your sum. So you would add up all the terms in between these two numbers. All right. And so here's some of the properties of sums. So again, if you have your sum multiplied by if it's c and your c is a constant, right, then your sum is just going to be c times n. So whatever this top number in your sequence is that you're adding up, whatever the constant is times that number, that's going to be your sum. Okay. The next one. Okay. If you've got the explicit formula multiplied by a constant, you can take that constant and multiply it by the explicit formula, then take the sum, or you can take the sum with the explicit formula first, and whatever you get for the sum, multiply it by the constant. It'll give you the same sum. All right. Here, if you've got two explicit formulas added together, right, and you're taking a sum there, then you can take the sum of the first term and then add it to the sum of the second term, and then you would still get the same answer. And likewise, if you're subtracting, you can take the sum of the first term minus the sum of the second term, and then you can get the same answer that way. So those are some of the properties of sums that we're going to be looking at. All right, so now we move into a discussion on the series. And so come to the definition. All right, so we have a sequence. Okay, the sum of the first n terms of the sequence is called the finite series, okay, or the partial sum of the sequence. All right, so if you're adding up the first several terms, a specific number of terms, that would be the partial sum, all right, or a finite series. Okay, so a series with an ending point, right, that you're adding up. The sum of all the terms of an infinite sequence is called an infinite series, right? And it's denoted with this notation. Notice right here in the sigma notation, what's the ending term that you add together? Infinity. Okay, it never ends. You add all of the terms together, all of them. All right? So you might be asking yourself, well, Coach, how can you get a sum if you're adding all the terms and the terms never stop? Well, sometimes you can't get a sum, right? Okay, so sometimes the sum is infinity, right? But sometimes you can get a specific, or you wouldn't say the sum is infinity, it just doesn't have a sum. Okay, and we'll discuss that more here in just a second. Okay? But anyways, you've got finite series, the series stops. Infinite series, the series never stops. And then so the sum of a finite series is called the partial sum. And then, of course, you can take the sum of all of the terms in an infinite series. So you can take the sum of the terms of a finite series or the sum of the terms of an infinite series. All right? Now, here's some other things to discuss on that. So we have examined the end behavior of functions before. All right? And so we've learned at times when the functions approach infinity, the ranges approach a unique number that's called a limit, right? And so an infinite sequence may also have a limit. Okay? If the sequence has a limit such that the terms approach a unique number, then that number is said to converge. If not, the sequence is said to diverge. All right, so let's wrap our head around this for just a minute. If a sequence has a limit such that the terms approach a unique number, then it's said to converge to that number. So what we mean by that is this. Okay, and if it doesn't, the sequence diverges. So in other words, as the terms of the sequence keep going on and on and on and on, right? If it has a limit, the terms have a limit, right? In other words, the value that each term is approaching has a limit, and it gets closer and closer to that number as the terms go on. You can say it converges to that number, right? So, like for example, if the first term in the sequence is 9.9, plus the next one is 9.99, plus the third one is 9.999, plus the fourth one is 9.99999. Then the further out you go, the closer those terms get to the number 10. It never gets there because 10 is the limit of what those terms approach. So then you would say that that particular sequence converges to 10. Does that make sense? All right. So if you've got a sequence like 2, 4, 6, 8, 10, 12, 14, 16, 18, the numbers in that sequence don't ever approach any certain number. They just keep getting bigger. They keep getting bigger and bigger. All right, so that sequence diverges. It does not approach a certain value. All right, so that's the difference between a convergent series and a divergent series. All right. Now, here's also a main point to remember. An infinite series only has a sum if its sequence converges to 0. If the sequence converges to 0. So if you have an infinite series, the only time it has a sum is if the sequence converges to 0. That means the more terms you get, the closer those terms get to 0. Like for example, let's say the first term is 1/2, then 1/4, then 1 over 8, then 1 over 16, 1 over 32, 1 over 64, 1 over 128. Okay? As that bottom number gets bigger and bigger in the denominator, those terms get closer and closer to 0. So that infinite series would have a sum. You would be able to find the sum. Okay? But if the sequence doesn't converge to 0, if it diverges, it doesn't have a sum. Or if it converges to some number other than 0, it doesn't have a sum. So the example that I used earlier with the 9.9, 9.999, 9.999, it converges to 10, but that infinite series still would not have a sum. Why not? Because it does not converge to 0. Okay? So let's do some examples and see if we can come up with, clear it up a little bit. So we're going to be asked to find the sum. Okay? So on this one, I want to find the sum of this formula, explicit formula. And so this formula, remember, will produce a series. And I want to find the sum of the first 5 terms of the series. I want to find the sum of a sub 1 to a sub 5, right? I want to find the first 5 terms of the series. Okay, so one way to do it is to actually write them out. So if I plug in a 1 here, then what's the first term going to be? Well, it's going to be 4 times 1 minus 3, plus the second one is going to be 4 times 2 minus 3, plus 4 times 3 minus 3, plus 4 times 4 minus 3, plus 4 times 5 minus 3. All right? That would be the sum. Simplifying it now, that's going to be 1 plus 5 plus 9 plus 13 plus 17. That will all add up to 45. Okay? So again, we want to add up the first 5 terms in this sequence. All right, so that's my sum. I want to show you something on Desmos here real quick that you may enjoy. If we go to functions and we come over here to miscellaneous, one thing I want you to notice, you've got the summation here. And so, yes, it will do it for us. So I want the sum from 1 to 5 of what? 4 n. Make sure you go and get your n, right? Minus 3. And there we go. It does it for us. And that is not the number I was expecting. And so let me see if I can correct that by doing this. There we go. All right, so you'll have to make sure that you put that number in parentheses, because otherwise it would take the sum of 4n, the first 5 terms of 4n, and then subtract 3 from that sum, which is not what you want to happen. You want this all to be included in the explicit formula. So the explicit formula is not 4n and then subtract 3 from the sum. The explicit formula is 4n minus 3. And so that's what made the difference. So make sure you're typing it in correctly. That whole thing has to be in a set of parentheses in order to get the right sum. All right? And as we can see, it's the same thing as what we got when we did it by hand. And so we're in good shape there. All right. Take a look at this next one, though. Notice that the terms that I'm adding up, the sum that I'm getting, does not start with the first term. So you don't always have to start with the first term. I want to add up terms 3, 4, 5, 6, and 7. All right, so by hand it would look like this. It would be 6 times 3 minus 3 over 2 plus 6 times 4 minus 3 over 2 plus 6 times 5 minus 3 over 2 plus 6 times 6 minus 3 over 2 plus 6 times 7 minus 3 over 2. All right? And so that's going to be 7.5 plus 10.5 plus 13.5 plus 16.5 plus 19.5. And then we can add all that up to get 67.5. Okay, once again, I can check that in Desmos, and it'll look like this. Okay, I want to make my adjustment here to the first term is 3, the last term is going to be 7. And of course I need to change this to 6n minus 3 over 2. And then of course it gives us the correct sum. Alright, so you can double check these in your Desmos calculator. It does have the summation notation in there. Alright. Now this one is a little bit different. This is the first infinite series that we've come to. And so remember what we said about infinite series. Okay? It only has a sum if the sequence converges to 0. So we need to test that first, because if this sequence doesn't converge to 0, then there is no sum. There would be no answer here. All right? So let's see if this thing converges to 0 or not. How can we tell that, Coach? Well, what we can do is we can look and plug in values here and see if the values get closer and closer to a certain number. And so I'm going to add another one here, and I'm going to put 7 over 10 raised up to, let's say, the first power. All right, so that's 0.7. What about second power? 0.07. Third power, 0.007. Fourth power. All right, and so on. So let's see what's happening here. When I write these terms out, it's going to be 7 over 10 to the first power plus 7 over 10 to the second power plus 7 over 10 to the third power plus 7 over 10 to the fourth power plus 7 over 10 to the fifth power plus, and then so on up to infinity, right? So let's see if we can tell if this thing converges or not. So this would be 0.7 plus 0.07 plus 0.007 plus 0.0007 plus, make sure I got the right amount of zeros in here, 0.02347, and so on. All right. Well, let's think about the sum of that. What would that add up to? Well, if I were to add all of these together, I've just got a 7 behind each placeholder here. So that's 0.77777, and it repeats the decimal behind it. All right. And so, really, that's the sum. But what I wanted to do is verify that it converges to 0, and it does, because look, the further these numbers go out, these terms go out, the closer that number gets to 0. 0.000007, 0.0000000007. So it gets closer and closer to 0. So the limit, as the terms in the sequence get large for the numbers in the sequence, is 0. The numbers in the sequence approach 0 the more terms you go in the sequence. And so since that's the case, since the infinite series converges to 0, the sequence converges to 0, we know it does have a sum, and this is the sum. All right? Now, can we write this as a fraction? The answer is yes. 0.777777 is actually 7 over 9. All right? And so that would be the sum of all of the terms in this sequence. So even though we can't physically add all the infinitely many terms together, right, we do know that they add up to 7 over 9. We do know that is the correct sum. Okay? Now, in the notation, okay, there is no summation notation here for infinity. I don't think there's any symbol for infinity here on this. But what you can do to estimate it is this. We can put 7 over, if I can get this, there we go. You can put 7 over 10, right, to the n power. 7 over n to the n power. And we start with 1. But there's no symbol for infinity that I'm able to find on Desmos. Perhaps you can find it. If you do, let me know, because I don't know where it is. Okay, but we can estimate what it would be, the sum would be, up to infinity by just putting a very big number in here. So once I put, a billion in there, you can see quickly that the sum is 0.7777777, which is the same thing here when we got it by hand, and we know that we can turn that into this fraction, okay, 7 over 9. Like I say, I think there's probably a fraction converter that you can find, decimal to fraction, online somewhere pretty quickly if you have trouble understanding that this is 7 over 9. All right? And so, again, that's kind of how it works with the sums of these series. All right? And so, important thing to remember, if it's a finite sum, right, a finite series that you're looking at, okay, it has a definite sum, If it's an infinite series, it may or may not have a sum, depending on whether or not the sequence converges to 0. Remember, if it converges to 0, then it has a sum. If it doesn't converge, if it diverges, if it doesn't approach a number with the sequence, it doesn't have a sum. And if it does converge to a number other than 0, it still doesn't have a sum. All right? So there you go.